Welcome back to another episode of Saltwater Stories. We are so glad you tuned in.
It's great to be back.
Now, usually when we get together, we tell you to grab your snorkel, check your air tanks, and, get ready to get wet.
Right, we're usually headed underwater.
But today's story is really out there.
Literally.
Literally. So we will need you to put away your scuba gear this week, and instead, I want you to mentally put on your spacesuits.
That is right. We are trading the wetsuit for the flight suit today. We are leaving the docks and heading for the launch pad.
I want everyone listening to close their eyes for a second. Come on, do it. We are going on a trip.
A pretty big one.
Imagine you are strapped into a giant rocket. You are lying on your back, looking up at the sky. You can feel the rumble of the engines beneath you. It's this deep feeling, deeper than thunder, shaking your whole body, kind of rattling your teeth.
And then you hear the countdown in your helmet.
The countdown hits 0, 3, 2, 1, and boom, you blast off.
You're just pinned to your seat by the force. You're leaving the ground, pushing up through the clouds, going higher and higher until the sky. Well, it changes.
How does it change?
Goes from that bright blue we all know to this deep, dark purple, and then finally into the silent black ink of space.
And you are floating now. Zero gravity. Your pencil starts floating right there in front of your face.
It's a pretty amazing feeling.
Now, unbuckle your seatbelt, float over to the window, and look back. Look back at home. Look back at Earth. What do you see?
If you ask the astronauts who have actually been up there, they all say the same thing. You don't see the borders between countries.
No lines on a map?
Nope. You don't mostly see green forests or brown mountains.
Yeah.
You see blue, a deep, dazzling, swirling blue. You see a water world.
You see the blue marble.
The blue marble, exactly.
And that is where our story begins today. We are looking at the ocean, but not from a boat bobbing on the waves. We are looking at it from the perspective of giants, using these robots that fly 17,000 miles per hour.
It's a huge shift in perspective.
Today, we are launching into the incredible world of satellite oceanography.
It really does sound like science fiction, doesn't it?
Yeah.
Like something out of a movie.
It totally does.
But it is very real. It's the science of observing our oceans from hundreds of miles above, using these artificial moons, these satellites that we have built and launched into orbit.
And to really understand why this is such a huge deal and why we build these, super expensive robots, we have to travel back in time a little bit.
Right. We need to talk about a specific robot, a true legend.
A legend. I like the sound of that.
Yes. The legend of CSAT. This is really where the story of modern ocean watching begins.
Okay, let's set the scene. The year is 1978.
A great year.
Maybe your parents or even grandparents remember this. Disco music is on the radio. People are wearing bell-bottom jeans. The first Star Wars movie is still a huge deal in theaters. And NASA decides to do something they have never done before.
Something revolutionary.
They launch a satellite called CSAT.
Now, you have to remember, before 1978, we had satellites. Of course we did.
Mm.
But they were mostly for weather, looking at clouds to see if it was going to rain, or they were spy satellites looking at other countries.
Okay.
But CSAT was different. It was totally unique.
Oh, so what made it special?
It was the very first satellite built only to study the ocean. That was its sole mission. It wasn't looking at anything else.
Just the water.
Just the water. It was basically a floating science laboratory in orbit. It had all these special sensors that could look at waves, wind, temperature, day or night. It's packed with gadgets.
So they launch it. It goes up on the rocket. It gets into orbit. It unfolds its solar panels, turns on its instruments, and
And it works. It works perfectly.
kind of amazing.
They start sending back all this incredible information. The scientists down on Earth are just ecstatic. They're popping champagne. They're celebrating.
It was a golden moment.
It really was a huge success.
So, but then the twist. Every good story has a twist.
The tragic twist.
It was what you'd call a tragic hero. CSAT worked perfectly for exactly 106 days.
That's it. Just about 3.5 months.
And then, zap. A massive electrical short circuit just fried its batteries. It went silent.
Gone. Just a dead piece of metal floating in space.
That sounds like a total failure.
It seemed like it at the time. The scientists were just heartbroken. They thought they had lost everything.
Yeah.
But here's the aha moment.
Okay.
When the scientists actually sat down and looked at the data CSAT collected in those 3 short months, they were absolutely shocked.
What did they find?
They found that in just over 100 days, that one single satellite had collected more data about the ocean than all the ships on Earth had collected in the previous 100 years combined.
Whoa, wait. Let me make sure I heard that right.
It's a big number.
100 days of this one satellite versus 100 years of all the ships sailing around the planet.
That is correct. Think about it. All the sailors, all the captains, all the scientific expeditions, all the logbooks written over an entire century
And one robot beat them all in a summer.
in a single summer.
That is bonkers.
It really is. And even though CSAT died young, it proved a point, a huge point. It proved that looking from space was the future. It completely changed everything about how we study the sea.
Okay, so to understand why a robot in space is so much better than a boat, we have to talk about the old way of doing things. I mean, humans have been sailing for thousands of years, right? Why didn't we know more?
We have been sailing, yes. But for a long, long time, the tools were, well, very simple.
Oh.
If you wanted to know how deep the ocean was, for example, you used something called the lead line method.
A lead line? That sounds heavy.
It was. You literally tied a heavy lead weight to a very long rope. You threw it overboard, waited for it to hit the bottom, which could take a while, and then you had to pull it all the way back up and measure how much of the rope got wet.
Ugh, that sounds exhausting. And so slow.
It was incredibly slow.
Mhm.
Think about the famous HMS Challenger expedition. That was way back in 1872. It was the first big scientific trip to study the whole ocean. They sailed around the world, and it took them 4 years just to do one lap.
4 years for one trip around. Wow.
And that brings us to the big problem. We call it the tyranny of distance. The ocean is just, it's too big.
It's massive.
It is. But to make it simpler, let's use the swimming pool analogy. I know you like analogies.
I do love a good analogy. Lay it on me.
Okay. Imagine the ocean isn't the ocean. Imagine it is a giant swimming pool. But, and this is a big, but it is a swimming pool the size of the entire world.
A world-sized swimming pool. Okay, I'm picturing it. I've got my trunks on.
And your job is to find out the temperature of all the water.
Okay.
In the ship method, you are in a tiny, tiny rowboat.
Yeah.
And you have one little thermometer.
Just one.
Just one. You dip it in the water, write down the number, and then you start rowing to the other side. You row and you row. By the time you get all the way across this world-sized pool, weeks or even months have passed.
My arms would be very, very tired.
Very tired. And here's the kicker. By the time you get to the other side, the water back where you started has already changed temperature.
Oh.
The sun went down, or a storm came through, or the heater turned on. You can never know what the whole pool is doing at the same time because you are just too slow.
You're always chasing a ghost. You're always behind.
Exactly. Now imagine the satellite method. You aren't in a boat. You are a lifeguard sitting in a really, really high chair, like way up in space.
The ultimate high chair.
And you have a special camera that can see the heat of the water. You can take a picture of the whole pool at once. You see the warm end, the cold end, and you see who is splashing in the middle all at the exact same second.
Okay. That's what you scientists call the synoptic view.
I think the fancy term is synoptic view.
Yeah.
It just means seeing the big picture all at the same time.
Right.
And it all comes down to speed.
Right.
A ship moves at maybe 15 miles per hour. A satellite moves at 17,000 miles per hour.
17,000. That speed is just mind-blowing. That's like crossing the entire United States in, what, 10 minutes?
Even less.
Yeah.
It's just incredibly fast. It can scan the whole Earth in just a couple of days.
But speaking of speed and flying,
Yeah.
how do these things actually stay up there? I mean, gravity is still a thing in space, right? Why don't they just fall down and crash into the ocean?
This is one of my absolute favorite things to explain. It's a branch of physics called orbital mechanics, but let's just call it falling forever.
Falling forever. That sounds terrifying.
It's actually really, really cool. Let's do another little mental experiment.
Mm-hmm.
Imagine you are standing on top of a super, super high mountain.
Okay, on a mountain.
You have a baseball.
Yeah.
Throw it gently. What happens?
It goes forward a bit, curves down, and thud, hits the ground.
Right. Gravity pulls it down. Now imagine you are the Incredible Hulk. You throw it much harder.
Okay.
It goes for miles and miles before it curves down and hits the ground.
Great.
Now, imagine you have a cannon for an arm and you throw that ball at 17,500 miles per hour.
That is a very fast pitch.
It is. At that speed, the ball is still curving downward toward the Earth because gravity is pulling it. But because the Earth is round, the Earth curves away from the ball at the exact same rate.
Something that never hits.
It never hits. It's constantly falling toward the ground, but the ground keeps curving away from it. It just keeps circling the planet forever.
So a satellite is just a robot that's falling sideways really, really fast.
That is exactly what it is. It's in a constant state of free fall around the world. And depending on how they fall or their orbit, they can do different jobs for us.
There are different kinds of orbits.
Yep. We usually use two main types for ocean satellites. Let's use an orange to visualize this. Do you have an orange?
I always keep an imaginary orange on my desk. Okay, I'm holding the orange. This is Earth.
Perfect.
Yeah.
The first type of orbit is the polar orbit. Let's call this the peeler.
The peeler, okay.
Imagine you take a marker and draw a line on your orange, starting at the top instead of the North Pole, going straight down to the bottom, the South Pole, and back up to the top.
Got it. One big circle.
Now, slowly spin the orange while you keep drawing that circle over and over. What happens?
Eventually, my marker line would cover the whole orange. Yeah, like I'm keeling it in one long, continuous strip.
Exactly. The satellite flies north to south, while the Earth spins underneath it. This is perfect for seeing the whole world every few days. It covers every single inch of water.
That makes sense. Okay, that's the peeler. What's the second type?
The second type is the geostationary orbit. Let's call this one the staring contest.
Huh. I'm really good at staring contests. I never blink.
Well, this satellite never blinks either. In this orbit, the satellite is much, much higher, up about 22,000 miles away.
Wow, that's far.
And it moves at the exact same speed that the Earth spins.
Mm.
So if you were standing on the equator looking up, that satellite looks like it is hovering motionless right above your head. It's staring at one spot constantly.
Why would you want to just stare at one spot? Doesn't that get boring for the satellite?
Not if you're watching something dangerous develop. It's perfect for watching hurricanes. You can watch the clouds swirl and grow in real time, 24 hours a day, because you never look away. You don't have to wait for the satellite to come back around the Earth. You just sit and watch the storm get stronger or weaker.
Okay, so we have these robots falling around the Earth, peeling oranges and having staring contests. But how do they actually see the water? I mean, they are hundreds of miles up. Is it just a really, really big zoom lens?
Sometimes.
Yeah.
But it's more than that. They have what I like to call super eyes.
Super eyes.
They can see parts of light that human eyes can't see. It's called the electromagnetic spectrum.
Is that like X-ray vision or something?
It's close to that idea. We usually break it down to two types of seeing or sensing, passive sensing and active sensing.
Okay, what's the difference?
Passive sensing is like taking a photo without a flash. You were just catching the light or heat that is already there, coming from the sun or glowing off the ocean itself. It's the satellite's camera.
Okay, so what can a camera tell us about the ocean from that far away? I mean, it's just blue, right?
But that's the thing. It's not just blue. The color of the ocean tells us a lot. It can be green or brown, turquoise, even red sometimes.
I've seen green water at the beach. I usually think that means seaweed or just yucky stuff.
Or it means phytoplankton.
Phyto what now?
Phytoplankton. They are tiny, microscopic plants that live in the water, billions of them.
Okay.
And they have chlorophyll, just like the grass in your backyard, which is green. So they turn the water green. We call them the grass of the sea. They are the base of the entire ocean food web.
So if the satellite sees green water, that means there's lots of food for the little fish.
Exactly. And the bigger fish that eat the little fish. And brown water usually means mud or dirt washing out from rivers near the coasts. So the satellite looks at the color and can tell us, hey, lots of fish food over here, or ew, that's really muddy over there.
That is super useful.
And the technology is getting so much better. The old satellites had what I call a crayon box with maybe 8 colors. They could tell blue from green, the basics.
A little starter box of crayons?
Right. But there is a new satellite that just launched called PACE, and it has 200 crayons.
200? That's the big box with the sharpener built into the back.
It is. It's what we call hyperspectral. It has so many colors. It can tell exactly which type of algae is in the water. It can tell the difference between good algae that feeds fish and a toxic red tide algae that can make people and animals sick.
No way. It can do that just by looking at the specific shade of green or red.
The specific shade. It's incredible.
Wow. Okay, what else can the passive camera see?
It can also see heat. We call it infrared or heat vision. Everything that has heat glows with a light our eyes can't see. The satellite's camera can. It sees the ocean glowing with warmth.
And why do we care if the ocean is hot or cold in a certain spot?
Because warm water is hurricane fuel. If we see a big patch of really hot water in the tropics, we know that if a storm passes over it, that storm could get much, much stronger. It helps us predict how dangerous a hurricane might become.
Okay, that makes sense. So that's passive sensing, just looking. What about the other one, active sensing? You called it the yeller.
Yeah, active sensing is the yeller. Think of it like a bat. You know how bats use echolocation? They send out a little squeak and listen for the echo to bounce back.
Squeak, squeak. Yeah.
Or if you stand in a big canyon and shout, hello, and you wait for the echo to come back.
Hello, hello.
Exactly that. The satellite doesn't wait for light from the sun. It makes its own signal. It shoots a signal down, usually a radar pulse, and listens for the bounce.
It provides its own flash for the picture.
A perfect way to put it. And the big advantage here is that radar is a superpower. It can shoot right through clouds.
Oh, that's huge, because whenever I look at a picture of Earth from space, it's covered in clouds.
The ocean is cloudy about 70% of the time. So if you only had a regular camera, you'd miss a lot. You'd just see the fluffy white tops of clouds. But radar goes right through them. It works day or night, rain or shine.
So we have the peeler, the staring contest, the camera, and the yeller. Now let's get into the nitty-gritty. What are they actually measuring with all this tech? I think you mentioned 3 big ones.
Yes. The big 3 measurements for physical oceanography from space are height, wind, and salt.
Let's start with height. This one honestly still confuses me. We are measuring the height of the ocean.
Yes, we call this altimetry, and it works using what I call the ping pong trick.
Ping pong, like table tennis.
Sort of. The satellite is the paddle. It shoots a radar pulse down, that's the ping. It hits the water surface and bounces back up, that's the pong.
Ping pong.
The satellite has an incredibly precise clock, and it measures exactly how long that trip took, down to, trillionths of a second. Since we know the speed of light, that time tells us the exact distance.
But light moves so fast, that must be a really, really good clock.
It is unbelievably precise. And get this, these satellites are flying 800 miles up in the sky, and they can measure the height of the ocean to within 3 centimeters.
Wait, say that again?
3 centimeters, that's about 1 inch.
From 800 miles up, they can tell if the ocean is an inch higher or lower.
It's like being in a jumbo jet and spotting a dime lying on the sidewalk. It is an absolute engineering miracle.
But wait, isn't the ocean flat? I mean, okay, there are waves, but isn't sea level just level?
That is a great question. And the answer is no. The ocean is definitely not flat. It has permanent hills and valleys.
Hills and valleys made of water. How does water stay in a hill shape? Why doesn't it just flow away and flatten out?
2 main things cause this. First, gravity isn't the same everywhere on Earth.
It's not.
Nope. The seafloor has huge mountains and deep trenches. A huge underwater mountain has a lot of mass, so it has more gravity. It actually pulls water toward it, creating a permanent hump of water on the surface right above it. We call this weird, lumpy, true shade of the ocean the geoid.
So there's a water hill over an underwater mountain. That's wild.
It is. And the second thing is heat. Warm water expands and takes up more space. So a pool of warm water actually stands taller than an equal amount of cold water.
So currents like the Gulf Stream, which are warm?
They are like rivers with a slope. The Gulf Stream is physically higher in the middle and on its edges. Water literally flows downhill in the ocean, from areas of high sea level to areas of low sea level.
That is amazing. I will never look at the ocean the same way. And I guess this is how we track sea level rise, too.
This is exactly how. We have been tracking it for over 30 years now with a series of satellites. The first was Topex Poseidon, then the Jason series, and the new one is Sentinel-6.
Sentinel-6, Michael Freilich. I love that satellite.
It's a fantastic mission.
It looks like a little doghouse.
It does. It looks like a little golden house flying through space. But it is our #1 guardian watching over our rising seas.
Okay, so that's height. Number 2 is wind. How on earth do you see wind from space? You can't see air. Air is invisible.
You are right. You can't see the air, but you can see what the air does to the water's surface. This is called scatterometry.
Scatter what now?
Scatterometry. Think of the mirror versus foil analogy.
Okay, I'm listening. Another analogy.
Imagine the ocean is perfectly calm, not a breath of wind. The water surface acts like a perfect mirror. If you shine a flashlight, or in this case a radar beam at it from an angle, the beam just bounces off and goes away from you.
Right, like skipping a stone, it just flies off into the distance.
Exactly. Not much of the signal comes back to the satellite. Now imagine the wind picks up. The water gets choppy and rough. It's covered in tiny little waves. The surface now looks like crumpled aluminum foil.
Okay, all wrinkly.
So now when you shine your radar beam on it, the beam hits all those little crinkles and scatters in all directions. A lot of it bounces straight back to you.
So the rougher the water.
The more signal scatters back. And rougher water means stronger wind. So by measuring the amount of that backscatter, we can calculate the wind speed and direction. This lets us find storms brewing in the middle of the ocean where there are no ships or weather buoys.
That is so clever. using the roughness of the water to see the invisible wind. Okay, the last big measurement. Salt.
Salinity. This one is the hardest one of all.
Why is it so hard? Can't you just taste it from space?
If only. No, salt is tough because it doesn't really change the color of the water. Yeah. It doesn't change the heat very much either.
So how do you measure it?
Well, it does change one thing. It changes the conductivity of the water, how well electricity can move through it.
So the satellite is zapping the ocean with electricity.
Not quite zapping, it's more like it's listening. The satellite measures the microwave glow coming off the ocean surface. Saltier water glows just a tiny, tiny bit differently than fresher water. A mission called Aquarius did this a few years ago.
How sensitive is that?
It is incredibly difficult. It's like trying to taste a single pinch of salt dissolved in a gallon of water. But you have to do it from space.
These robots are way smarter than I thought, so we can see height, wind, and salt. We can see color and heat. But what does this actually do for us? I mean, besides making really cool maps for scientists to look at.
Oh, it does so much. These satellites they're basically superheroes. They save lives, they catch bad guys, they protect the planet.
Okay, let's start with saving lives. I heard a story about a teenager. I think her name was Abby Sunderland.
Yes, the Abby Sunderland story is a perfect example of the Search and Rescue Satellite System, or SARSAT.
Set the scene for us. What happened?
So it was 2010. Abby was only 16 years old, just a few years older than some of our listeners. And she was trying to do something incredible. Sail around the world all by herself.
Wow, at 16.
She was in the middle of the Indian Ocean, one of the wildest, most remote places on Earth, thousands of miles from land.
And something went wrong.
Something went very wrong. A rogue wave, a giant wall of water, hit her boat. It was so powerful it snapped her mast right off. Her boat was crippled, dead in the water in the middle of nowhere.
That is my absolute nightmare. So scary.
But she was prepared. She had a special yellow box called an EPIRB, an emergency position indicating radio beacon.
An EPIRB.
She flipped the switch. That box started sending out a distress signal, a simple help beep out of space.
And a satellite heard her.
A satellite in that polar orbit we talked about passed overhead, and it picked up the beep, and then it did something really clever. It used the Doppler effect.
The Doppler effect.
You know how an ambulance siren changes pitch as it drives by you? It goes wee woo woo.
Yeah.
The satellite used that change in the pitch of the beep as it flew over her to calculate her exact location on the globe. It sent those coordinates to a rescue center. A French fishing boat and an Australian plane were guided right to her tiny boat in that massive, massive ocean.
And without the satellite.
Without the satellite, finding her would have been like finding a needle in a haystack the size of a continent. She survived because of space tech. And that system has saved between 48,000 and 60,000 lives.
That gives me chills. That's amazing. Okay, so they save lives. You also said they catch bad guys. Are we talking about space police?
You could call them that. We call them the detectives. They look for two main things: oil spills and dark fleets.
How do you spot an oil spill from space? Is it just a big black blob?
It can be, but the radar sees it even better. Remember our mirror versus foil analogy?
I do. Calm water is a mirror. Rough water is foil.
Right. Well, oil is thick and gooey. It calms the waves down. It makes the water surface super, super smooth.
So it turns it into a mirror.
Exactly. So on a radar picture, the rough, windy ocean looks like a fuzzy gray, but an oil spill looks like a black, smooth blob against that gray. It stands out perfectly. We can track exactly where the spill is going and help the cleanup crews.
And what about these dark fleets? That sounds very ominous.
It is. These are illegal fishing boats. They go into protected areas where they aren't supposed to be. To avoid getting caught, they turn off their tracking systems. They go dark so the authorities can't see their dot on the map.
Super sneaky.
Very sneaky. But they forget one thing. Their boats are made of metal. And metal reflects radar very, very well.
Ah. So they shine like a diamond on a black cloth.
They shine like a bright white dot on the radar map. So the authorities look at the satellite image and say, hey, there's a ship right there on the radar. But no ship is reporting its location. Busted.
You can run, but you can't hide from the radar satellite. That is so cool.
Satellites also help us protect animals and the climate in so many ways.
I know they track sea ice, right? That seems really important for polar bears.
Yes. And radar is perfect for that because it can see the ice day or night, which is crucial because the North and South poles are dark for 6 months of the year. We have a continuous record of how the ice is shrinking.
What about somewhere warmer, like coral reefs?
The satellites act like a fever thermometer for the reefs. NOAA has a program called Coral Reef Watch. The satellites take the temperature of the water over the reefs every day.
Okay.
If the satellite sees the water getting too hot for too long, it sends a bleaching alert to the park rangers on the ground.
So they can go out and help the roof.
Exactly. They might close the area to tourists or change fishing rules to give the coral a break so it has a better chance to recover.
I even heard we can track whales from space. Can we actually see a whale? It seems too small.
We can't usually see the whale itself, you're right, but sometimes we can see what they leave behind. We can see the biogunk.
Biogunk. That sounds gross.
It is a little gross. It's their poop plumes.
We're tracking whale poop from space.
We are. When a pod of whale surfaces, they leave a trail. And we can see that change in the water color from space. Or more commonly, we can track the electronic tags that scientists put on their fins.
That is hilarious, whale poop from space. Science is glamorous, folks.
That really is.
So we've talked about the past with CSAT and the present with all these superheroes. What about the future? What is the next big thing in satellite oceanography?
The future is all about detail and teamwork. We have a new mission that is just incredible. It's called SWOT.
SWOT. What's that stand for?
Surface Water and Ocean Topography. Think of it as the high-definition upgrade for our ocean maps. The old altimeters we talked about measured a thin line directly below them, like a pencil line. SWOT measures a wide path, 75 miles wide. It sees the ocean in beautiful 3D detail.
And it looks at rivers and lakes, too, right?
Yes, that's what makes it revolutionary. It's the first satellite designed to really measure fresh water on land. It will measure millions of lakes and rivers all over the world. It's effectively weighing all the water on Earth.
So it will help with things like floods and droughts.
Like never before.
And are the satellites themselves changing? Are they getting bigger or smaller?
Smaller. Definitely smaller. We are moving toward CubeSats. These are tiny satellites. Some are the size of a shoebox.
A shoebox? How can a shoebox do the job of a giant satellite?
Well, you don't use one. Instead of one giant bus-sized satellite that costs $1 billion, imagine launching a swarm of hundreds of these little shoeboxes.
A swarm of bees flying together.
Exactly. They fly in formation. If one breaks, it's no big deal. The others carry on. And because there are so many, they can take pictures of the ocean every hour instead of every few days. We are building the Internet of the Ocean.
The Internet of the Ocean.
Imagine satellites talking directly to underwater drones, automatically sending them to investigate an oil spill without a human ever touching a button.
That sounds like science fiction again.
It's happening right now. It's the future we are building.
Wow. So let's just try to unpack this whole journey we've been on. We went from dropping heavy lead weights on ropes, which took years to get one measurement, to having swarms of shoe boxes and golden dog houses flying 17,000 miles per hour, shooting lasers and radar at the sea.
It's been an incredible evolution in a pretty short amount of time. These satellites, they really are the silent guardians. They are up there right now as we were talking, taking the ocean's temperature, checking its pulse, and watching over the sailors and the whales.
They connect everything, the ocean, the atmosphere, and us on the ground.
They really do. And you know the best part? The data is free.
Free? What do you mean free?
All of this data from NASA and European satellites is open to the public. Anyone can look at it. You, listening right now, can go online and see the temperature of the ocean near your house. You can track a hurricane in real time.
That's a really cool thought.
It is. And I want the listeners to realize that this isn't just for adults and lab coats. Maybe you'll be the one sitting in mission control one day. Maybe you'll be the one decoding the secrets that these robots send down from the stars.
That's a great thought to end on. The next time you see a wave at the beach, just remember a robot 800 miles up is watching it with you.
It's a nice thought. We're never really alone on this blue marble.
Well, spacesuits off, everyone. We are back on solid ground.
Safely landed.
Once again, thanks for tuning in, and we look forward to having you back next week for another incredible episode of Saltwater Stories. Bye for now. Take care.
Goodbye, everyone.